Thank you. I love getting applause, even if I haven't done anything yet. That's great. I love it. Thank you. Okay, I'm really excited to be here. My name is Dr. Talitha Washington. I have the privilege of being the president of the Association for Women in Mathematics. And today we are going to have an amazing Emmy Noether lecture given by Dr. Neena Gupta of the Indian Statistical Institute. Let me just, yes, clap, clap, clap. Professor Neena Gupta, in the Theoretical Statistics and Mathematics unit in the Indian Statistical Institute, is recognized for outstanding contributions to affine algebraic geometry, for creating deep theories and rich expository that have attracted many mathematicians to the field, and for being a brilliant problem solver who successfully solved one of the most challenging and long-standing open questions of nearly 7 decades. The Zariski cancellation problem. Discovery of this bridge itself is a landmark with enormous potential. More broadly, Neena has been making masterly contributions in the area of affine fibrations, including a structure theorem for locally Laurent polynomial algebras, a beautiful analog of the theorem for locally polynomial algebras due to the Bass, Connell, Wright, and Suslin. In other landmark paper in Transactions of the AMS, Neena presents an infinite family of counterexamples to a conjecture of M. Miyanishi on the invariant subring of a polynomial ring under the additive group GA, a topic closely related to Hilbert's 14th problem. And as an applied mathematician myself, I think I too will be attracted mostly to what she will talk about today, as you will as well. She's been recognized with a number of high honors, including being invited as an ICM 2022 sectional speaker in 2 sections, algebra as well as algebraic and complex geometry. In 2019, Neena earned the distinction of being the youngest ever mathematician to be awarded India's highest scientific honor, the Shanti Swarup Bhatnagar Prize. She received the ICTP Ramanujan Prize in 2021 for her outstanding work in affine algebra, algebraic geometry, and commutative algebra, in particular for her solution to the Zariski cancellation problem for affine spaces. I really look forward to her presentation today, and she will give a talk on, let's see if I get it right. Okay, we'll see. The Abhyankar-Sathaye, there we go, conjecture for linear hyperplanes, and I can't think of a better way to spend my birthday than to have you be on Noether lecture. Thank you. So give her a round of applause. So I'll hand a certificate to you after that.
Oh, great. Thank you. Thank you. It is indeed a matter of great pleasure and honor for me to give this 2025 Emmy Noether lecture. Thanks. Thank you, Talitha, for this introduction. Let me begin my talk. Today, I will be talking on this Abhyankar-Sathaye conjecture for linear hyperplanes. And before that, we should pay our tribute to Emmy Noether. In fact, I drew a lot of inspiration from the life and research of Emmy Noether, and she has largely shaped our modern algebraic thinking. I don't know, but it's unlike Emmy Noether, who was never encouraged being a female to do mathematics, and she had a very tough life. I was very blessed, and I was guided by, with big help and support from my family, from my colleagues, from my teachers. I have been always supported, and never in my life I felt that I'm being a female, I'm being discouraged to do maths. So yeah, and when I was a student, I'm still a student, I must say. I'm trying to learn various things, but when I was introduced to the subject of commutative algebra, I was enjoying it a lot, and later I came to know it was she developed this subject. She is the founder, And today I'm feeling very emotional that I could finally come all the way to give this talk. And with honoring my request, the stalwarts in the area of affine algebraic geometry, especially Professor Miyanishi, came all the way to attend this conference. Thanks for making it a big success. And I work in the area of affine algebraic geometry, which is in the interface of commutative algebra and algebraic geometry. And these are some challenging problems in the area. My work touches some of these problems except the first one. And the main ingredient or the tool which we use to attack these problems are the theory of GA action, where GA is the additive group K plus, where K is a field on an affine variety. And sometimes we also use K theory. And again, it was Emmy Noether. She gave the very basic fundamental results on group actions on algebraic varieties. So let me first say the two main difficulties which we come across while solving this problem. The first one is to determine whether a given polynomial f is a coordinate. So that is, if given a polynomial f, can you find f2, f3, fn, n minus 1 polynomials, which will generate the polynomial ring kxn up to xn along with means f will generate that. So that is a very difficult problem, and once you go for n greater than 2, this becomes almost impossible. And of special interest are the ones which are polynomials which are linear in one of the coordinates. We will see by example why they are important. Another difficulty which we come across is to find a useful characterization for a ring to be a polynomial ring. So this again is a very challenging problem, and if we have a solution to this, or effective solution to this, we can resolve many of the problems. And of special interest are the rings A, which are obtained from a polynomial ring by quotienting a linear polynomial. These are some notations. Throughout my talk, K will denote a field of any characteristic, and for any field f, f bar will denote the algebraic closure of f. And for a ring R, A equal to R square bracket n would mean that A is a polynomial ring in n indeterminates over R. So let me begin with the epimorphism theorem, and paying our tribute to Sriram S. Abhyankar, who is a pioneer in the area of affine algebraic geometry. So this is some theorem which I can even state to almost all the participants who is present here. I can tell what the theorem is. So you just take two polynomials u and v over a field k, which is a non-constant polynomial, such that you can get t from u and v by some polynomial combination. So this is something I can even state to a high school student. Then the epimorphism theorem says that either the t degree of u divides the t degree of v, or the t degree of v divides the t degree of u. It is the most celebrated, highly non-trivial theorem, and known as the epimorphism theorem. It's known in much more generality in positive characteristic also, but I will not get into that. This immediately gives you this theorem, which is written in ring theory language. So for knowing theorem 1, you don't even know what is a ring. But theorem 2, suppose you have a surjective map from a polynomial ring in 2 variable to a polynomial ring in 1 variable. And if n is the t degree of phi x and m is the t degree of phi y, both of them greater than or equal to 1, then either m divides n or n divides n. And this gives us the epimorphism theorem, which was also proved independently by Suzuki for complex numbers. That is, if you have a polynomial f such that the 0 set of f defines a polynomial ring in 1 variable, then f must be a coordinate. So this is a problem in 2 variables. We can generalize this theorem and ask a problem in higher variables dimension, that if f is a polynomial in n variables and the 0 set of f defines a affine n-1 space, does that necessarily imply that f is a coordinate? And the epimorphism theorem says that yes, it is true in characteristic 0. However, counterexamples were known as early as in 1956, 57, and later by Segre, and later Nagata gave a family of examples of non-trivial lines. So he, for example, he constructed this polynomial G, which is a special type here. You can see here P is the characteristic of the field, and if you take such a polynomial G, then this G satisfies that G is give rise to a polynomial ring, quotient of G is a polynomial ring, but G is not a coordinate. Such a G we will call a non-trivial line by some abuse of notation, and the famous Abhyankar-Sathaye epimorphism conjecture asserts an affirmative answer to this problem in characteristic 0. However, this problem is completely open, but it has been seen that for some special cases, we can ask this conjecture even in arbitrary characteristic. The first case for n equal to 3 was considered by Sathaye over characteristic 0 and Russell for arbitrary characteristic. They considered G, which is a linear polynomial in Y, and suppose G defines an affine plane, they proved that G is a coordinate. In fact, they proved much more. They proved that you can find a coordinate x1 in x and z such that the coefficient of y is actually a polynomial in one variable, and G is a coordinate along with x1. More precisely, they proved that any linear plane in AY will be of this form for some chosen coordinate x and z of A. We can ask this problem in higher dimensions, and for example, we can say, what if you take a polynomial G of this form which defines a polynomial ring, whether G is a coordinate along with x. As an while working on this Zariski's cancellation problem, we obtained this result for when Ax is of this special type. Now, there are other results which have been considered for n equal to 3 by David Wright, Prosenjit Das, Datta, Russell and Sathaye, Kaliman, that for instance, David Wright considered this case of A y to the power n minus b, and then Russell and Sathaye considered this case where the coefficients of this y, the GCD is not equal to 1, GCD is not a constant, and Kaliman in fact went to a different direction. He proved that if the general fiber of G is an affine plane, then G must be a coordinate. Now we can ask a question of generalizing the Sathaye-Russell theorem in higher dimension and take a polynomial h of this form, kx up to xn is a linear polynomial in Y, and consider this ring A, which is B mod h, and ask these questions: under what condition this ring A is a polynomial ring, and if suppose A is a polynomial ring, does that necessarily imply that h is a coordinate? That's a epimorphism theorem. And if A happens to be a polynomial ring, whether h will be a coordinate along with xn up to xn. We have obtained some affirmative answer to this question under certain assumptions on alpha, this coefficient of y and this polynomial f, in joint paper with Parnashri Ghosh and Ananya Pal. But the first discovery for the m equal to 1 case was taken care by Kaliman, Venero and Zeidenberg as early as in 2003, and they obtained this result over the complex number field where they considered f to be of this type, which is a linear polynomial in Y, and the coefficient of Y is a polynomial in two variables. And they proved that if f defines an affine 3 space, then if any of this condition is satisfied, then f is a coordinate. Unfortunately, their result is not completely solves the linear polynomial case, and At the end, I will exhibit an example. So recently with Parnashri and Ananya, I dealt with the case over a field of arbitrary characteristic, and we obtained that if the leading coefficient of y(ax) has no simple root, so means all the roots of ax has multiple root, then we obtained that this ring B is a polynomial ring if and only if f is a coordinate. So that's a kind of answering the Abhyankar-Sathaye conjecture for in arbitrary characteristic. And further, in this case, f is a coordinate along with capital X. And this theorem also tells you that this f is a coordinate we can easily determine by this last condition, which is very useful, that such an f will be a coordinate if and only if this b lambda zt is a coordinate in the field, extended field k lambda, where lambda is any root of A. For example, looking at this theorem, we can immediately rule out that if a ring is determined, if the zero set of this G1 can never be a polynomial ring, or the zero set of G2 can never be a polynomial ring, because here b lambda zt is given by this z square plus t cube, which can never be a coordinate. So we can immediately rule out examples of rings which cannot be a polynomial ring. Now this question must be there, that why consider only linear polynomials? The conjecture is for arbitrary polynomials. But it has been seen that some major breakthroughs in the area of affine algebraic geometry has been concentrated on linear polynomials. The first example was of this Russell cubic, which is a linear polynomial in Y, and for quite some time it was a threat for mathematicians to know whether this ring A is a polynomial ring, and finally Makalimanov proved that this ring is not, and later Makalimanov and Kaliman, they showed that none of this Korus-Russell threefold are polynomial ring, which eventually led to the solution of the linearization conjecture for C star action on C3. So for a long time this was a very difficult, challenging problem, and it is still challenging, this Russell's cubic, because one doesn't know whether this ring is a stably polynomial ring or not. If it's a stably polynomial ring, then we have a counterexample to the Zariski's cancellation problem in characteristic 0. So that will be a... Anyway, so my solution to the Zariski's cancellation problem also involved this ring A, which was discovered by Asanuma, which is also given by a linear polynomial. So, and this threefold was involved in the questions on affine fibration problem and the linearization problem in positive characteristic were studied by Asanuma. So let me first describe what is an affine fibration problem. So this is a very simple problem for any ring R and a prime ideal P of R. Let's use this notation K round bracket P be the field of fractions of the integral domain R mod P, or it is a residue field of the local ring RP, and A tensor Kp is the fiber ring of the A. And this is a natural question to extract information about the R algebra A from the fibers of A. And so we call a ring A to be an AN fibration over R if A is flat and finitely generated over R, and it satisfies that all the fibers of A are polynomial rings. So let me reiterate, it is all the fibers of A is a polynomial ring. And this famous conjecture or problem by Dolgachev and Westphaler asks that suppose R is a regular local ring of dimension D, does that necessarily imply that any AN fibration is necessarily a polynomial ring? So following this Dolgachev and Westphaler conjecture, some positive results have been obtained. So the first non-trivial theorem was proved by Kambayashi and Miyanishi for n equal to 1 for any dimension, and Professor Datta, he was my supervisor, who proved it that it is enough to assume this condition on the fibers only on prime ideals of height at most 1. And it's a highly non-trivial result due to Sathaye, that any A2 fibration over a one-dimensional regular local ring is necessarily a polynomial ring if R contains the field of rational numbers. However, Asanuma constructed example to show that no, it is not true if R does not contain the field of rational numbers. So it is not even true if R is equal to Z. And this problem of affine fibration is open for higher dimension, for even for n equal to 2 and d is equal to 2. And this Asanuma and me has given some counter examples when R does not contain the field of rational numbers, that we have examples of A2 fibrations or arbitrary rings which are not necessarily polynomial rings. The most complete result which has been obtained by Asanuma in this direction is that for a regular local ring, any characteristic does not even need rationals or anything, any AN fibration is a stably polynomial ring. So in case we are looking for counterexamples to the cancellation problem, we should better look at counterexamples to the affine fibration problem. And this was the example of Asanuma, which he constructed in 1987 in the context of A2 fibration problem. And he proved that this ring A is an A2 fibration over the polynomial ring Kx. This ring A is a stably polynomial ring, but A is not a polynomial ring over the subring Kx, where small x is the image of capital X in A. Therefore, A is a non-trivial A2 fibration over the PID Kx. However, in 1994, Asanuma revisited this example again in the context of linearization problem, and he asked whether A is itself a polynomial ring over K. And if yes, then it would have given rise to a non-trivial K star action on the polynomial ring K3 in positive characteristic. And if no, then it would clearly be a counterexample to the Zariski's cancellation problem, which I will discuss in the next slide. And Peter Issel called this dichotomy as Asanuma's dilemma. And I was very fortunate that Asanuma sir visited us ISI, and I could noticed his example and work with him. And I proved that this Asanuma's ring is not a polynomial ring whenever this integer r is greater than or equal to 2. So this immediately solves the Zariski's cancellation problem, which asks that if you have an affine variety V, and after adjoining one dimension, it becomes an affine n space, does that necessarily imply that V is an affine n space? And algebraically, you can ask that if you have a ring, after adjoining one variable, it becomes a polynomial ring. Does that necessarily imply that A itself is a polynomial ring? And this is a diagram which has been illustrated by my Ananya Pal and for affine plane. So geometrically, it means that if you have a variety and you look at a cylinder over this, adding one dimension, suppose it is isomorphic to the affine 3 space, does that necessarily imply that V itself is an affine plane? So that is a cancellation problem. It is difficult to visualize in higher dimension, but probably this is the best approximation. And Zariski, who laid the foundation of modern algebraic geometry and connected it with commutative algebra. So this problem was known to have an affirmative solution by Abhyankar, Inikin, and Heinze. Their result was much more general for n equal to 1. And in a non-trivial, highly non-trivial work by Miyanishi, Sugi, and Fujita, gives an affirmative answer for the affine plane in characteristic 0, which was also generalized by Russell over perfect field. And with Bhatwadekar sir, I could resolve the case of arbitrary characteristic, arbitrary field K, need not be perfect. And this research on the Zariski's cancellation problem had led to beautiful topological characterization of the affine plane by C.P. Ramanujam and algebraic characterization of the affine plane by Miyanishi, which eventually led to the solution of the Zariski's cancellation problem for the affine plane. So he is C.P. Ramanujam, who gave the topological characterization of the affine plane, and Miyanishi and Russell, who were involved in the cancellation for the affine plane proof. And I showed using Asanuma's example and later generalizing it in higher dimension that over a field of positive characteristic, the cancellation problem does not hold for n greater than or equal to 3. However, it is still an open problem in characteristic 0 for any integer n greater than equal to 3. So this research on, and for n equal to 3, this asynchronous threefold has provided the counterexample. And the research on the Zariski's cancellation problem had opened up its connection with other important problems, the affine fibration problems and the embedding problem. Now I come to the embedding problem, the generalization in higher dimension towards my results. So this problem we have discussed, why linear polynomials. Now this is the setup. K is any field, B is this polynomial ring, H is a linear polynomial, and A is this quotient ring. And the question is to determine conditions for A to be a polynomial ring. If A is a polynomial ring, can we answer the epimorphism problem? Or if, in this case, can we say, generalize the Sathaye-Russell theorem and say that H is a coordinate along with x1 up to xn? So we have solved these cases, and let me illustrate it with my first result with Parnashri Ghosh. So for a field of arbitrary characteristic and G be a polynomial of linear polynomial in Y, then we obtained that whenever these integers R1, R2, Rm are greater than 1 and capital F is of this special type, then the following statements are equivalent. That is, this ring A is a polynomial ring if and only if your small f, which is the projection along the line x1 to xm, is a coordinate. If and only if this G is a coordinate along with x1 up to xn. And recently we generalized it for any coefficient of y, alpha, y1, y2, yn, x1 up to xm, but here we take characteristic of the field to be 0. So we proved that under the assumption that every prime divisor of alpha divides this H, then suppose this ring A is a stably polynomial ring, or in fact, and this curve kzt mod f, this the curve defined by this is a regular ring. Then f is a coordinate, in fact, and moreover, H is a coordinate along with xn up to xn. Now it may look a bit kind of this condition, something non-usual, why one should look at this condition. So we have something more. We suppose we don't assume that special condition, and we assume, so we take alpha to be the coefficient of y and factorize it. So this condition that f is a smooth curve can be obtained if any of these conditions is satisfied. That is, so the simplest is your alpha consists of one simple prime factor. In that case, your f has to be smooth and your epimorphism problem will work. Or if suppose all the factors are multiple roots, so all the prime factors of alpha are multiple prime factors, then if any of these conditions is satisfied, which I will not get into, then we obtained the equivalence of following statements. That is, this ring A is a polynomial ring if and only if its capital H is a coordinate along with xn up to xn. And for that it is enough to assume that A is an A2 fibration over kxn up to xn, or it is just enough to assume that A is a stably polynomial ring. So this family of hypersurface H is very big, but for a special case, we can consider any such alpha and any f is included in this family. Now I come to the main part, that is the GA actions, the action of the additive group K plus. And if we write it algebraically, it is can be written in terms of ring homomorphisms, which is known as exponential maps phi u from A to AU, satisfying the following two axioms of the group action. So the first one is the identity, that is this composite map is an identity on A where epsilon 0 is the evaluation at u equal to 0. And the second one is the additive function, that is if we have phi v, which is the exponential map, and if we extend it to AU by sending U to U, then phi V compose phi U is phi V plus U. So it is just the algebraic analog of writing the additive action of K plus on an affine variety over an algebraically closed field. So for example, for an exponential map phi on A, we can define the ring of invariant, which is the subring of A generated by, it's not generated, it is this set itself, that all those elements in the ring A where phi of A is equal to A. It's a subring of A. So let me give you a very quick example. So for example, this polynomial ring Kx, we can define an exponential map phi u by sending x to x plus u. It is an exponential map, and one can easily see that in this case the ring of invariant is K. So the group actions give rise to many invariants in the ring, and this invariant was discovered by Dugson. So an exponential map phi is said to be non-trivial if the ring of invariant is not equal to the whole ring. And the Dugson invariant of A is a subring of A generated by the ring of invariants of all exponential maps of A. For example, it is denoted by dk of A. For example, the Dugson invariant of any polynomial ring must be the whole ring if n is greater than 1. We can see that if A is a polynomial ring kxn up to xn, and if I define phi I to be the map which sends xi to xj to xj plus this Kronecker symbol delta aj times u, then each of this phi I for I1 to n is an exponential map, and in this case the ring of invariant is the kxn up to xi minus 1, except the ith variable is missing. And so if you have n is greater than 1, you have I and j, two different I and j that will easily generate the polynomial ring. And in general, it is very difficult to compute the Dugson invariant, but for polynomial ring, it is very easy to see that it is the whole ring. Another important invariant, which was given by Makalimanov in the context of this, when he solved the Russell's cubic problem. So it is a subring of A, which is obtained by the intersection of ring of invariants of all non-trivial exponential maps on A, and it is denoted by Makalimanov is ML of A. And one can see very easily by the previous result itself that for Makaliman invariant of a polynomial ring must be K only, constants. So it's the same exponential map. If you look at the intersection for I equal to 1 to n, then it is K. Now another technical term which I have to define to illustrate my next theorem is R divisible. So we call a polynomial alpha in m variables R divisible, where R is some set of integers R1, R2, Rm, if there exists a system of coordinates xn up to xm such that you can write alpha as x1 to the power R1 x alpha 1, and every time you can, once you project xi is equal to 0, you can divide it by xi to the power Ri. So let me quickly give it an example. For m equal to 1, we say a polynomial alpha is R1 divisible if you can write it as in this form. So here R1 is an integer greater than 1. For m equal to 2, it would mean that you can express it as in this form, x1 to the power R1 plus something x2 to the power R2, where R1 and R2 are both greater than or equal to 1. And so for example, this polynomial alpha is 2,3 divisible in the x2, x1 coordinate and 1,6 divisible in x1, x2 coordinate. For m equal to 3, we say polynomial is R1, R2, R3 divisible if alpha can be expressed like this, where the last one alpha 4 is a constant. In fact, I made a mistake. In alpha 4, it may be some element in k, it need not be just constant. It's a constant, okay, yeah, it's a constant, non-zero constant. So similarly, you can define inductively for m equal to 4, it would look like something like this, where alpha 5 is a constant. So with Pornoshri and Ananya, we gave this result that if H is a linear polynomial in Y, with alpha being R divisible, and capital F breaks like this, that fzt minus x1 times any arbitrary polynomial. So this is anything arbitrary. Alpha is R1, R2, Rm divisible, but each Ri is greater than 1. Then this ring A, suppose I assume that the Maclaurin invariant of A is either K, which is similar to the polynomial ring, or the Dixon invariant is the whole ring. Then one can find a system of coordinates Z1, T1 of the polynomial ring KZT and some polynomials A0 and A1 such that this FZT is a linear polynomial in T1. So this is one of the very important, crucial result, and it immediately gives you criteria to decide whether some rings are not a polynomial ring. For example, if you look at this polynomial where A can be any polynomial, and this coefficient of Y is 2 divisible in X, and F is Z square plus T cube, so which cannot be made linear in any system of coordinate. So this polynomial H will not define affine 3 space. Even if by a choice of A, you can make this ring as nice as possible. For example, if I go to higher dimension, take this coefficient of Y, it looks very cumbersome, but and beta is any arbitrary polynomial, but we know that small fzt cannot be linear, and therefore this zero set of H can never define an affine 4 space. And with choice of beta, you can make this variety smooth, unique factorization domain, contractible, means you can have as many nice properties as you want, but this can never be a polynomial ring. So we obtained this theorem, that is, if alpha is an R divisible polynomial, and suppose all prime factors of alpha divides H, then we proved that so if K1 is the extension of K by these roots lambda 1, lambda 2, lambda m, not roots. So basically, when I say alpha is R divisible, so alpha is R divisible in some extended coordinate system. It need not be from the base field. So this lambda 1, lambda 2, lambda m did not come from K. So here K is a field of any characteristic, need not even assume algebraically closed, but you have to assume that K1 over K is separable. So under this assumption, we obtained an equivalence of 14 statements. So the first 5 statements are the most attractive ones, which tells you that this H is a coordinate if and only if this ring A is a polynomial ring, and the easiest way to judge whether H is a coordinate comes from just looking at this polynomial ring in 2 variables and this small f, kzt. And if I assume that the Maclaurin invariant of this ring A is trivial, that means ML of A is K, then these conditions are also equivalent. That is, it's a stably polynomial ring, it's a small f is a line, and A is an A2 fibration, and and this one, so this one is probably the most fascinating for giving a characterization of the affine plane, that if I assume that A tensor K bar is UFD, the Maclaurin invariant are trivial and the units of this are trivial. So this is probably the least assumption which we can take to A to be a polynomial ring. So for example, this family of polynomials contains this hypersurface, which is an R1, R2, Rm divisible, and it also contains polynomials of this form where the coefficient of Y is A1, X1, AM, XM, where all these A1, A2, Ams have multiple roots. And as a consequence, we have several positive results. So the first one I would like to say is that if you consider any ring of this type, where A is pi 1 to the power s1, pi n to the power sn, so where and capital F is of this type, then this ring A is a polynomial ring in m plus 2 variables if and only if your small f is a coordinate, and it provides a general framework for understanding the non-triviality of the Russell-Chorus threefold as well as the generalized Asanuma varieties, because this is a theorem on arbitrary characteristic. It works for complex, it works for positive characteristic. And it also tells you that generalizes this Russell-Sathaye linear planes to higher dimension, that if this G defines a coordinate, I think I made a mistake here, this G must be capital F. Oh no, yes, I'm right. So this G is, okay, so this G is AY minus F. Okay, so this G is a coordinate along with x1 up to xn. So this gives a partial case to the Abhyankar-Sathaye conjecture. Further, we proved that for a field of arbitrary characteristic, if I take capital F to be of this type, and A is some product of primes where all these integers s1 up to sn are greater than 1, then this ring A is a polynomial ring if and only if it is a polynomial ring over the subring kx up to xn. So we have non-trivial A2 fibration if and only if small f is a non-trivial line. So whenever you have a f small f a non-trivial line, you could get an example of a non-trivial A2 fibration over kx up to xn. And this I proved using ideas of Asanuma, that if I take any ring R, which and some primes P1, pi 1, pi 2, pi n in R, such that RZT mod pi GZT defines a line, then such a ring D will be a stably polynomial ring for any set of integers. So after adjoining one variable, it will become a polynomial ring in 3 variables over R. And with Purnashri and Ananya, I got this theorem that whenever f is a non-trivial line, so let me put it this way. Whenever f is a line, we know that this ring A is a polynomial ring, and if f is a non-trivial line, the theorem of Purnashri and Ananya will say that A is not a polynomial ring. So thus, over a field of positive characteristic where you have non-trivial lines, you have counterexamples to the Zariski's cancellation problem. And with Purnashri, I also gave a classification of these rings. So what we do is that if you take x1 to the power r1, xm to the power rm minus fzt, where f is any non-trivial line, then 2 such rings are isomorphic if and only if this r1, r2, rm is equal to s1 up to sm up to some permutation of f and g. So this r1, r2, rm is equal to s1 up to sn up to some permutation, and f and g are equivalent. So we obtained an equivalence of 2 such rings. And thus, we can vary these integers s1 up to sm and r1, r2, rm, and we can find an infinite family of non-isomorphic rings, all of which become stably isomorphic to the polynomial ring. Because after adjoining one variable, it follows that they are polynomial ring. So we have an infinite family of counterexamples to the Zariski's cancellation problem. So another direction which one can look for is generalized the epimorphism theorem, and which was obtained by Bhattacharya sir, and he proved that for a Noetherian ring of characteristic 0, if you f defines a line, then f must be a coordinate whenever either R contains Q or R is a semi-normal domain. So semi-normal domain is here I am assuming R is a characteristic 0, so in particular this result is true even when R is Z. In the mixed characteristic, this is also true. And recently, Asanuma and Professor Datta, they proved that the hypotheses are necessary, that we have to assume both of these hypotheses. Another direction, so this is a generalization of the Russell-Sathaye theorem for rings. So the first generalization was obtained for a discrete valuation ring, and again their result was not complete. They solved it in some cases, that if you take G to be a linear polynomial in Y, and such that Rxyz mod G is R2, under the assumption that, so this can be proved that the coefficient of G will be a polynomial in one polynomial x0. So this x0 is a generic coordinate which need not be a coordinate. So there are examples which says that x0 need not be a coordinate. And they proved that this G will be a coordinate if we assume that the regular parameter of R, that is T, does not divide A, or if A is power of T. They have other cases also, but I will not get into that. And I will end my talk with this case of Bhattacharya and Datta, which they could not solve. And so this is, you take a polynomial ring in one variable, and A to be a polynomial ring over R, and F to be a linear polynomial in Z. You can see this is a linear polynomial with coefficient of Z is T times X square, and B to be the subring RF. Then they proved that A is an A2 fibration over B. So B is a two-dimensional regular ring. A is a stably polynomial ring over B. Further, this polynomial F defines an affine 3 space. That is Rxyz mod F is R2 so in particular it is C3. So F is a linear hyperplane in C4. And they left this problem asking whether A is a polynomial ring over B. And if you are familiar with this, this is this Venn-Arrow polynomial for m equal to 1. And we can ask in particular whether F is a coordinate, which is a linear polynomial. Note that F defines a plane, affine 3 space, which is a linear polynomial, and one doesn't know that whether F is a coordinate. And this was a case left by even Kaliman, Venn-Arrow, and Zedenberg. And if the answer is no, then we have counterexamples to all these 3 problems, which are open for a long time. Finally, I would like to pay my tribute to my supervisor, Professor A.K. Datta, Professor Bhattacharya, and Professor Abhyankar-Sathaye, who had largely shaped my academics, research, and my development, were very crucial, without whom I would not have been doing such piece of work. Thanks. These are some references.